I think I can say
a little bit powerful examples, a little bit more subtle examples. So, last time we talked about different rules for derivative. Rule for product, rule for quotient, rule for sum difference. We get some examples given a formula which is product of quotients of sums of differences, so maybe once again products of quotients of some familiar functions like x to the power n, e to the power s. So how to find the derivative? So I won't repeat it. You must solve exercises with different kinds of formulas and make yourself pretty proficient at just finding derivatives of complicated expressions. Today I want to start with such an exercise. My function is not given to me, but I do know something about it. Its value at the point 3 is, at the point 5 is 3, derivative is 4. And I'm also given another function. G at the point 5 is 2, G prime at the point 5 is 5. So if a new function h of x is f of x, g of x, e to the power x, find h prime at the point 5. So now I'm not given explicitly what the functions f and g are. I'm only given, some particular data. Their values at the point 5 and their values of their derivatives. And for instance, it's very easy to compute what is the value of this function h at the point 5. For this you have just to take the value of f at the point 5 times the value of g at the point 5 times e to the power 5. So that's easy. But the question is, what is the derivative of this function at the point 5? Okay, so maybe any ideas how to do it? Yes, exactly. So my function is a product of two functions which I don't know and a function that I do know. So the natural idea, let's try to apply the product rule and see how far it gets us. So solution, what is the derivative of h? Well, it's the derivative of the product f of x, g of x, e to the power x. Okay, I know product rule for a product of two functions. F times g prime is f prime g plus f g prime. Here I have product of three functions. F times g times e to x. What can I do about it? Take what?
Your e to the power x is derivative of e to the power x. Yes. You got to do it.
So derivative of e to the power x is e to the power x, but it doesn't, it doesn't really help me. I still have a product of three things which I wanted. Yes.
I'll use the product rule.
Okay.
Like, except.
Well, I know what you mean.
Use the product rule to solve the first Q,
Yeah.
and then you do the product rule of the whole.
Okay, yes. So the idea is to combine parts of this expression. I do have product of three things, but I can write it as a product of two things, and then the result gets multiplied by e to the power x. So let me apply it like this. This is f times g. I will think about it as just one function times e to x. So what do I get? It's the derivative of the first factor times the second one plus the first one times the derivative of the second one. So once again, the idea is I take just this part, f times g, and I think about it as just one function, one large unknown function. And I multiply it by e to the power x. Now I have product of two functions, and I apply the product. F times g prime times just e to x plus first factor as this times derivative of the second factor. I'm still left with derivative of some product, but now simpler one, just product of two things. So I apply my product rule once again. F of x, g prime of x, multiplied by e to the power x, plus f of x, g of x, and only now I use that derivative e to x is e to x. And maybe let me simplify it by just taking e to x out of all the brackets, f prime of x, g of x, plus f of x, g prime of x, plus f of x, g of x, and all this multiplied by e to the power x. Okay, so we performed some computation. We can't really simplify much further from here. I mean, we already got f prime at some of x, and basically we don't know what is f prime of x. We don't know what is f of x, we don't know what is g of x. But we can try to find what is the derivative of h at the point 5. Now let's plug in x equal to 5. So h prime at the point 5. What is it? Well, let's see. It's f prime at the point 5, which is 4, times g of at the point 5, which is 2, plus f at the point 5, which is 3, times derivative of g at point 5, which is 5, plus product of the two values, 3 times 2, times e to what power? 5, right. So my x is now 5, so I plug in x equal to 5, and I use this information about f and g and their derivatives at the point 5. And I get some answer. This is 8, 15, 6, 15, 23, 6, 29, times e to the power 5. Okay, so basically that's the answer. So what this exercise tells you, you can apply product and quotient rules even if you don't really know something about one of the factors or several factors or about the whole expression. So if the expression is a product, you can apply the product. If the expression is a quotient, apply the quotient. Same about sums, differences, and of course our favorite known functions. Another thing. Well, so maybe some comments about this. So we encountered a derivative of a triple product. And I mean, we might do this trick once, but we also might as well derive it once and just use it. So let me write it like this. If you have product of three functions and you want to find the derivative, the answer is like this. It's derivative of the first one times product of the other two plus the first one times derivative of the second plus times the third one plus f1, f2 times 3 prime. And in general it works for any number of factors. If you want 4 things, well, you'll have 4 sums like this. If in each element, you have derivative over one of the functions, and all the rest can as they are. Another comment may be even more important. I mean, this comment is good. It allows you to save time in some situations, but of course you can just forget about it and use this trick instead. Just combine some of the factors to one big factor and apply the usual product. Another comment which is very important. You should not, in such situations, simultaneously try to find the derivative and plug in numbers. This just is going to confuse you. So in the most extreme case, if you try to first plug in all the numbers and then find the derivative, then you just produce, I mean, obvious nonsense. So my comment is, if you want to compute such a thing, do not do the following thing. It's not the same as f to the point 5 times g to the point 5 times e to the power 5 and then derivative. No, not at all. Why not? Well, this thing is just a number. Once you plugged in a particular value for x, you forgot about the function. Now you have just one number. And derivative of one number is always 0. So this thing is just always 0. Regardless of the problem, regardless of the functions. And of course, that's not what you want to do. You want to first find all the expressions for the derivatives, and only in the very end plug in the numbers. So don't try to plug in numbers prematurely. Okay, so now maybe any questions about this problem? So we've seen an example where, well, the product rule is applicable and it's very useful for us. I want an example, well, sometimes product rule is actually not applicable. So I want to give you a opinion when it is applicable and when it is not. So another example exercise. So my function is now x times absolute value of s. And the question is, what is its derivative? And your first impulse might be, well, it is a product of two singular functions, x and absolute value of x. Let's try and just apply the product. So I would say it's almost a solution. You will see what's wrong there. I mean, it almost gives you the correct answer, but there are some problems. So an attempt would be like this. The derivative of a product is, well, x prime times absolute value of x plus x times derivative of absolute value of x. Well, x prime is 1, so I have absolute value of x plus x times, now what happens? Absolute value of x, what is its derivative? Minus 1 and plus 1, right? For some parts, well, for x which is negative, you know it's a line of slope minus 1. For x which is positive, we get an answer of 1. For x which is 0, well, we know that derivative does not exist. So, in a way, we do get an answer. But two things. One thing, the answer looks somewhat ugly. The second thing, which is maybe even more important, we still don't know what happens at the point 0. The reason is, well, product rule doesn't quite tell you about the situation when one of the factors is not differentiable. It might happen that somehow this factor is not differentiable, but the product is still differentiable. So we've got an answer for any point except 0. At the point 0, we still have to do some work. Yeah.
Like you said, the second term absolute x plus x multiplied by the second half of the function. But isn't it absolute x plus 1 because you're taking the derivative of x?
So this is x prime times absolute value of x. So it's derivative of x times the second one plus x times the derivative of the second one.
Oh, okay.
This is just round bracket. This is now 1. Okay, so the problem with this solution is the point 0. Let's try another one, another approach. Let me first simplify my function a little bit and then try to find its derivative. Maybe, okay, yes. So let me do it like this. F of x is x times absolute value of x. I can rewrite it. When x is non-negative, absolute value of x and x is just the same thing. So I get x squared. When x is negative, what happens? Absolute value of x is, how can you rewrite it? X with the minus sign, right? So when x is negative, it itself is some negative number, but we want to make it positive, so we add another minus sign. So here we get minus x squared. Okay, good. So now derivative of f, well, still will have some problem. When x is positive, we'll have 2x. When x is negative, we'll have negative 2x. Well, at 0, we might have some answer, but we aren't quite sure. Because, well, at the point 0, our derivative we'll use both definitions somehow. Both this one and that one. So we can't really tell from just looking at this formula what is the derivative at the point 0. But we can try to find it using just the definition. It's the limit as x goes to 0 of my function at the point x minus the function at the point 0 divided by x minus 0. So what is it? It's the limit as x goes to 0. X is the absolute value of x divided by x. So it's just absolute value of x. At least for any x which is not equal to 0, which is okay. My x is small, but not quite 0. And what about this limit? Limit of absolute value of x as x goes to 0. What is it? 0, right. When x is small, absolute value of x is still small. So as x approaches 0, absolute value of x also approaches 0. So it turns out that my derivative does exist at the point 0. regardless of what, well, of our inability to apply the product, it just exists from the very definition. So f prime in the point 0 is 0. You might wonder how it is possible. Well, let me draw a picture for you. I have a function which is f squared for x which is positive, and it is defined by a different formula, negative x squared when x is negative. Well, even though the two formulas are different, they do fit in very nice. First of all, the function is continuous. I can go from here to here without lifting my chalk off the board. And also it is differentiable. Means I don't have to change direction abruptly at any point. I go to here, now the direction is almost horizontal, here it is exactly horizontal, and they continue still in horizontal direction. So it's as if, well, a train that changes lanes. It can go at one rail and another rail, but if it does it smoothly, well, then there are no problems. So here it does do it smoothly. Okay, so the point of this exercise is to emphasize, well, product rule and quotient rule and everything is very nice when it works. And when exactly does it work? Well, if each one of the factors is differentiable, if each one of them has a derivative, then the product rule, quotient rule, all the rules do work. But sometimes it might be that the whole thing, the whole expression is differentiable, but each one of the factors isn't. So let's consider another kind of puzzle of the same kind. Maybe first questions about this. So let's have a puzzle of the following kind. Can f over g be differentiable everywhere? But prime and 0 and g prime and 0 both do not exist. So this question asks about similar situation to what we have just seen, but even worse. So in this situation we had two functions, their product was differentiable, but one of them was not, at least at one point, 2.0. Here it's a question about, is it possible that both functions are not differentiable, but their quotient is differentiable? So any ideas how, any opinions, is it possible or not possible? Or ideas how to construct such examples, or ideas why it's not possible? Any ideas? Yeah? So the question is not about the quotient itself. So first of all, nobody told you that f and g are both 0 and the point 0. And another thing, what is f over, I mean, the question is about differentiability, which means the actual, the quotient is, well, has a derivative. So it's about derivative of the quotient, not the quotient itself. So, not quite. Other ideas? many of you think, well, not think, but kind of feel that the right answer should be that it is possible for such a quotient to be differentiable? Okay, how many feel that it's not possible to be differentiable? Okay, so, well, at least this example should tell you that, yes, strange stuff can happen. So, it must tell you that somehow, well, in this situation, maybe if we try a little bit harder, we will be able to get something of this sort. So, my idea would be here to write the following. Well, I have lots of freedom. I mean, let me try to construct an example of two functions, both not differentiable at 0, such that quotient is differentiable. I have lots of freedom. I can choose any two functions. And, I mean, I know lots of functions. I have a huge amount of freedom. So I can use part of it to just get rid of part of the problem. So I want the quotient to be differential. Let me fix the quotient. Let me only look for such examples where the quotient is my favorite function which is differentiable everywhere. So anyone please come up with a function which is differentiable everywhere. Parabola. Well, okay, yes. So we'll look at okay, yes. We'll look. So that's not the solution, that's just an attempt. Look at G such that f of G is well, might be a good beginning. So at least for such functions, the quotient will be differentiable everywhere. But now we have still a problem. We want the two functions to be not differentiable at the point 0. So now we have to come up with some functions which are not good. So this function x squared is really, really good. What about a function which is not good? Absolute value of x. Okay, so absolute value of x, we know it's not differentiable at the point 0. Okay, so here we have such thing. Well, we already have some relation on f and g. Can we try, well, f absolute, well, we can try either f being absolute value of x or g being absolute value of x. Well, it turns out both will have a problem. So try g of x is absolute value of x, for instance. Well then, f of x will be x squared absolute value of x. That's not really bad, but the problem is the quotient being x squared absolute value of x divided by absolute value of x. Well, it's not exactly x squared. It is x squared for every x which is not equal to 0. But at 0 it's not defined. I mean, what happens at 0? If you try x equal to 0, you'll get 0 times 0 divided by 0. But you can't divide 0 by 0. So at the point 0, it's not defined. So you might be getting closer to a solution, but not there yet. So problem not defined at 0. And we also see the source for this problem. Our choice for this non-differentiable function, well, we want it to be in denominator. But in denominator, we don't allow things which are 0 at some points. So let's try to come up with a function which is not differentiable and also not 0. Any ideas? So I want some So something is maybe a corner, like epsilon value of x, but also such that it's never 0. E of x. So E of x is good, but it is differentiable.
Yeah.
Well, if something has to be not 0 at any point, it should be either always positive or always negative. So you should remember, you should try to imagine a graph kind of in upper half plane with a corner at 0. 2 to the power of x, no, still differentiable. It's very, very nice to curve. 1 over x is not good because it's not definable at 0. And we want something which is, well, x to the power what? X to the power 3 is still differentiable. It's given to us 3x squared. Yes, let's just take this thing and lift it up a little bit. The problem is it touches the x-axis. Let's lift it up. So nothing potential being. Let's try g of x is absolute value of x plus 1. Okay, then f of x is x squared times absolute value of x plus 1. Okay, now it looks much better. Indeed, f of x divided by g of x is x squared of any x, or all x. The quotient is differentiable. G prime at the point 0 does not exist. I mean, obviously, like for the absolute value of x, it doesn't exist. There might be still a problem. F prime at the point 0, well, I won't check it now, but actually it does not exist. So, it does exist. Unfortunately, no. F at the point 0 exists. Let me not actually perform this calculation, but maybe let me perform this calculation. It's not that hard. So I'll continue here. Limit as x approaches 0. Well, if I want the derivative of this function, I'll have to compute function at the point x minus function at the point 0, which is 0, divided by x. So its limit as x approaches 0, x times absolute value of x plus 1. And you see this limit is 0. So the problem is somehow, well, by being maybe unlucky, we made the function f well divisible by x. If it were not divisible by x, then we would have no problem. So the problem with the function f is that with this particular x squared. So now let's repair this problem as well. Where does this x squared come from? It comes from our very first choice. F over g is x squared. Somehow we were extremely unlucky with this choice. Almost every other choice would have worked. Except, well, x to some big power. So let us try the quotient to be different. Let me try it to be, say, identically 1. So let me take f of x, we just absolute value of x plus 1, g of x to be the same. So instead of starting with quotient which is x squared, let me take it to be just 1. Then obviously f of x over g of x is always 1. F prime at 0 and g prime at 0, well, both are the same thing and both do not exist. Okay, so the lesson you should take from here is, well, sometimes you are going to wonder whether something is possible or not, and you have no idea is it possible or not. So you have to somehow, well, in general, you have to somehow follow two approaches simultaneously. One, try to construct some examples or counterexamples to whatever you are trying to decide, and then also try to prove what is proven. So you have to take two roads simultaneously, and well, sometimes you are going to get some predicted differences along one of them, or both of them. So you should attack a little bit in one direction, in another direction, and try to overcome difficulties as they come.
For the answer, is it possible if it can be just absolute x or of x and g of x as well?
So with absolute value of x without this plus 1, no, it's not going to work because the quotient will be 1 for x which is not equal to 0 and not defined for x equal to 0. So it will not be differentiable at the point 0. But in this way, everything works. Okay, and well, just kind of, there will be problems, say, even on the standard midterm of the format, decide whether the following is true or not, and either explain why it is true or give a counterexample. So that's quite typical of such questions. Okay, so any questions about this? I want to talk a little bit more about well, this distinction between continuity, differentiability, when the derivative exists. So another exercise on similar ideas. Function is given by such a formula: ax plus b when x is negative, c times e to the power x when x is greater or equal than 0. And the question is, for what values of a, b, c, f is f prime of 0 is. So the question is whether for such a function defined by two cases, the derivative at the point 0 exists. So first of all, let me try to sketch how a typical function of this kind looks like. It is for negative x, it's part of a line, something like this. Maybe it's not quite here when x is equal to 0, and then it is exponential function times some constant, so it looks something like this. Okay, so that's how the function looks like, and we want somehow it to be differentiable at this point. So one, I would say, obvious attempt to solve such a question would be, let's try to follow the definition. Let's write the derivative at the point 0. So one attempt would be f prime at the point 0 is limit x goes to 0 of f of x minus f of 0 divided by x minus 0. Then figure out that to compute this limit, we'll have to compute two limits from the right and from the left and make them agree. So limit from the left is, well, I'll use this value at 0 is right here, when x is equal to 0, f of 0 is c times e to the power 0, so it is c divided by x. This should exist, and it must be equal to the limit from the right. Once again, c e to the power of x minus c divided by x. Well, and then you'll have to make some conclusions about the values of a, b, c, and the values of these limits. It's a good beginning. The problem is some of these limits are pretty hard to compute. So for instance, this limit is hard. But the good thing is, well, somehow we already encountered such limit in computational derivative. So it's hard to compute, not impossible, so it is kind of a good beginning of solution, but well, frequently it will be pretty hard to follow. So let me suggest another one. Another suggestion. So another suggestion is as follows. I want my function to be, well, kind of smooth without any corners and without any breaks like this. So I would want it first to be continuous so that this graph will not have any breaks. And then, well, so first I reported want f to be continuous and have no corners. Oh, that's exactly what I want. I want the graph to look, well, very nice, very smooth, without any breaks, any sudden changes of direction, any corners. So one of these things is very easy to understand. What does it mean that the function is continuous? Well, it's continuous everywhere except at point 0, where we have to compare the limits from the right and from the left. So continuity is very, very simple condition. We want limit as x goes to 0 from the left of f of x to agree with limit from the right of f of x and both to agree with the value at 0. That's exactly the continuity, and well, very easy to find both limits. Limit from the left is limit as x goes to 0 from the negative side of f of x. I use ax plus b. So it is just b. The limit from the right, I'll use the other definition. C times e to the power x. Well, e to the power 0 is 1. When x is close to 0, e to the power x is close to 1. It is c. And function of the point 0 is, I'll use this definition. Next is equal to 0, it's c times e to the power 0. It is c. So continuity, f is continuous. Precisely when b is the same as c, well, and the same as c here. B, well, I just need b to be the same as c. Now, so this is maybe not the hard part of the question. The harder part is, what about corners? We might still have, oh, so now we made sure that this line does meet this strange part of the graph, this exponential function at the right point, so that to go from one to the other, you won't have to make a jump. But you might still have to make a very inconvenient turn like this, which is a corner, different directions. So what I want to avoid is kind of this tangent line to this graph, being different from that tangent line to the other part of the graph. But I don't know how to find both tangent lines. I can just use the derivative. So the problem of corners, what is this tangent solution? So let's see. F prime at any point x, I can just compute the slope of the derivative at any point of x. Well, maybe except 0, because at 0 I might have problems. So it is a when x is negative, and when x is positive, it is so what is the derivative of c times e to the power x? C times e to the power x, right? So c is for me just a number. I still don't know it, but it definitely does not depend on x. So I can use the rule that derivative of constant times a function is constant times derivative of this function, and derivative of e to x is e to x. So here I have my derivative, and I want the two things to match precisely at the point 0. I don't want this situation when one of them does not match the other one, and they create a corner. I want them to smoothly go from one to the other. So we want the limit from the left of f prime x to be equal to the limit from the right. Because that's the slope of the tangent to the left part of the graph at the point 0. And that's the slope of the tangent to the right part of the graph at the point 0. And we want them to agree. So we want A, this thing, to be equal to this thing, C times e to the power 0. Well, that's it. When A is equal to C, well, first of all, when B is equal to C, we'll get a function which is continuous, no breaks. When, in addition, A is equal to C, we'll get a function with no corners as well. Something like this. It will have this part of the graph, which is exponential, and then it nicely transitions to a line, like this. So at this point, this tangent line will be exactly the same as this tangent line. So answer A must be the same as B, it must be the same as C, and each one of them are any numbers. So we just combine the two conditions that we found. B must be the same as C, A must be the same as C, but otherwise no additional constraints. So all three of them should agree, and that's it. So in this problem, the idea was, well, I do have a function which is actually complicated. It has some exponential functions and so on. So directly computing the value of derivative at the point 0, well, using limits would be complicated. But instead, we did the following trick. We first made sure that the function, the graph of function, doesn't have any breaks, which means the function is continuous. And we are now, well, pretty proficient with this continuity. In second part, well, we computed the derivative everywhere else but at the point 0. And at the point 0, we just made sure that the two definitions, two tangent lines, do match together. They don't, it's not that one of them is pointing in one direction, the other one is pointing in the other one. When they exactly match together, well, we have a smooth function. So that's the condition for matching together. No. Questions about this? One additional remark. We got some conditions about A, B, and C, but we didn't get the actual numbers. And it is, well, it happens quite often. I mean, you might get some conditions on your parameters, but get infinitely many different answers. So for instance, in the simplest example, when A is the same as B is the same as C, and all of them are equal to 0, well, you can just see that the function is identically 0, and you do get an answer. So at least you can see that for one value of these parameters, you do get a function which is very nice. But actually, for any other values of these parameters with this constraint, well, you still are going to get a nice function, something like this. Okay, so we've talked a little bit about the kind of subtle points of when to apply product rule, differentiability, continuity, such things. Now we are going back to basically just formulas about derivatives. So more formulas. This time I'm not going to derive anything, I'm just going to tell the answer. If you want to find the derivative of logarithm, well, it is 1 over x. Maybe later when we discuss chain rule, we'll be able to actually get this kind of, well, from the corresponding derivative for e to x. But for now, well, just remember, derivative of 1 is 1 over x. To be even more precise, it's not quite 1 over x, because logarithm is only defined with positive numbers. So this only for x which is positive. It's not an important remark, but well, let me draw the corresponding graphs to see that at least it's reasonable that the derivative logarithm is of this kind. So logarithm looks like this. For positive x, well, when x is 1, it is 0. When it's smaller than 1, it's negative and becomes very, very negative here. And then it grows, but pretty slowly. And derivative well, how would it look like? Positive, increasing, and yes, positive and decreasing, and right here it becomes kind of almost zero. So far away it's almost zero. It is decreasing, and right here it is very large. Here the tangent line is very steep. So when x is small, it is very large, and it decreases all the time. So actually it does agree pretty well with this graph function y1/x, except, well, function 1/x is defined not only for the positives. So it has another range right here. Yes, the whole shape is called a hyperbola. But otherwise, well, you see, yes, the derivative of logarithm makes sense that it is 1/x. And of course, well, there.
The parabola goes down or?
It's not parabola, it's called hyperbola, and it does go down. It approaches zero without ever becoming zero. And here it also approaches the y-axis without ever crossing it. And of course, well, when you have a new formula, you can apply the usual rules and get some results. If you want to take the derivative of 1 of x over x, well, just apply the quotient. So it's derivative of 1 of x times denominator minus 1 of x times derivative of denominator, which is 1 divided by x squared. So it is 1 minus 1 of x divided by x squared. And well, you can come up with arbitrarily complicated examples of this kind. Just now we have one more function which we can derive. Okay, so maybe any questions about derivative of logarithm? Okay, we have two more important functions. They are not as important in kind of finance, in economics, but they are important in physics, engineering, so we will introduce them. They appear every time we have some oscillations. For example, I don't know, some pendulum or oscillations of current in plug. So every time we have some oscillations, well, such functions tend to appear. The functions are sine of x and cosine of x. So let me first just talk a little bit about what sine and cosine are. Hopefully just a reminder. And then their derivatives. So first of all, what sine and cosine are. If you have a circle with radius 1, and you have some angle alpha, this height is called the sine of alpha. This distance, the horizontal distance, is called cosine of alpha. So for every angle, I compute two numbers. One is called sine, the other one is called cosine. And if you want to draw the graph of sine, say, well, when angle is 0, sine is 0. This height is 0. Then it starts increasing a little bit, all the way until 1 here. Then it starts decreasing, keeps decreasing, then it starts repeating itself as you make more circles. And it continues in this way to the left as well. These heights are of course 1 and negative 1. So here we have peaks of sine and minimum of sine. So it continues in this way all the way to infinity. for 0, this point, well, in calculus we measure angles in a funny way. We measure them not in degrees, we measure them in what's called radians. So radian is basically like this. We say that such a thing, well, we measure angles by kind of length of arc. If this is a circle of radius 1, we say that this angle is phi. And then we measure all the rest, well, proportional. So if we say have quarter of a circle, we say its angle is pi by 2. So to be honest, it's not an angle, it's just length. It's length of this arc. Length of this arc is exactly pi. But of course, I mean, it doesn't matter whether we say an arc of length pi or half a circle. It's the same thing. So here we have pi by 2, well, maybe 3 pi by 2, we'll also switch here. Pi plus another couple of pi. So this is 3 pi by 2. So these things are pi by 2, pi, 3 pi by 2. And starting from 2 pi, we have repetition. Here we have minus pi by 2, minus pi, and so on. So that's how sine of x looks like. There is a similar picture for cosine of x. Cosine of x, well, when x is 0, it is 1. Then it starts decreasing a little bit. Then it drops all the way to -1 at pi. Then it increases all the way to 1 back at 2 pi. And it repeats itself. So this is pi by 2. This is 0, this is 1, this is -1. This is 3 pi by 2. Minus 2, minus 5. So basically what you should know about sines and cosines are, well, more or less this picture and these graphs. So this graph and this graph. And the particular features. It is, say, cosine 0 at 0, at pi, 2 pi, at 3 pi, basically at any multiple of pi. So you should know at least this. And you should know the derivatives. So it turns out, well, first observation, the function sine is repeating itself. As you make one full rotation, it starts repeating itself. So its derivative must be repeating itself. And it turns out it is exactly cosine. So what you should remember is derivative of sine is cosine, derivative of cosine turns out to be negative sign. So you should remember which one of them has negative sign. And well, you can also see from the graph. For instance, here cosine when x is small and positive, cosine is decreasing, so its derivative must be negative. So it's not the sign, it's minus sign. Well, and basically that's all you should know about sines and cosines. And of course, once again, once we know such formulas, we can compute lots of other things. For instance, if you want to find what is the derivative of a function which is called tangent, it's sine over cosine. So what is the derivative of sine of x over cosine of x? Well, here you have a quotient, just apply the quotient. So it's derivative of sine times cosine minus sine times derivative of cosine. I started to take the place, move to the other one. Derivative of quotient sine over cosine, derivative of sine times cosine, minus sine times derivative of cosine, divided by square of cosine, well, derivative of sine is cosine, so here we have cosine of x multiplied by itself, minus derivative of cosine is negative sine, so we have another negative sine. So a total plus sine squared of x divided by cosine squared of x. So basically in our course, that might be an answer. In general, well, it turns out that this expression can be simplified. If you look at this circle, and you know Pythagoras theorem, you'll notice that sine squared, distance squared, like distance squared is distance squared, which is exactly 1. So from some geometry, you can conclude that this is in fact 1 over cosine squared of x. And of course, well, you can come up once again with arbitrarily complicated expressions, with sines, cosines, e to x, ln of x, powers of x, find all their derivatives. Yeah. You should memorize those, you should memorize derivative of logarithm, you should memorize derivative of e to x and x to the power x. So all the same. This is okay, other questions? Okay, so let's start our quiz. So the question says follows. F of x is square root of 1 minus x. Find the derivative at the point A. Well, in the domain A is smaller than 1. Using the definition of derivative. So no other method will be accepted. Only definition of derivative. Yes, definition using limits. Yes. Second question is, the graph of f looks like this, kind of a bump like this. And the question is, sketch the graph of f prime. maximum of this function is when x is equal to 0. Yeah.